Welcome to the deep dive. Imagine you're the lead developer for a booming e-commerce site. Business is great, but lately users are complaining. Checkout is slow, dashboards lag, and everything just feels sluggish. You suspect the database, but where do you even begin? Today, we're cutting through that complexity. We're diving into excerpts from Vlad Mihalcea's high-performance Java persistence book, a true masterclass, really, in diagnosing and solving these kinds of database bottlenecks. Our mission for you today is to pull out the most impactful strategies, maybe some surprising facts that can turn that sluggish application into a high-performance machine. So if you've ever felt, overwhelmed by database performance issues in Java, this deep dive is definitely for you.
That's a perfect scenario to frame our discussion because, as the source points out, more than half of application performance bottlenecks originate in the database. I mean, that's a staggering statistic. It just highlights how critical that data access layer really is.
More than half. Wow.
Yeah. So we're going to unpack some practical techniques to tackle these bottlenecks, starting right from the foundation, the database connections, all the way up to some advanced ORM optimizations. So yeah, let's peel back the layers on this one, the database connectivity foundation. Connections and pooling.
All right, let's start right at square one. How Java applications even talk to databases. The source material emphasizes that while Driver Manager can give you physical connections, it's incredibly expensive. Why is pooling so much faster? What's the actual cost we're dodging here?
Well, the critical insight here is that opening and closing database connections is a deeply expensive operation. Just think about it. It's like setting up a brand new secure communication channel every single time you want to send a tiny message.
Right.
You've got TCP connection overhead, there's authentication, and then there's the constant allocation and deallocation of temporary memory buffers, both on the client and the server side. So reusing these connections via a pool, it completely sidesteps this repeated high-cost setup and teardown. The book highlights benchmarks with Hikari CP. That's one of the fastest pooling solutions out there, showing connection acquisition time with pooling is between 2 and 4 orders of magnitude smaller.
2 to 4 orders of magnitude.
Yeah. Smaller than establishing a fresh connection. That's not just an improvement, it's monumental.
Okay, so that's huge. Pooling isn't just a nice to have, it's basically essential if you want that e-commerce checkout to feel snappy, not sluggish. But this brings up a common question. How do you even figure out the right size for your connection pool? The book mentions queuing theory, capacity planning, and something called Little's Law. That sounds pretty academic.
It can sound academic, yeah, but Little's Law, often written as L-Z-M-E-L-A-W, is actually a really profound but simple rule of thumb for any queuing system, really. Think of it like a busy coffee shop. L is the average number of customers inside the shop, right? That's our connections in use. Is how fast new customers are arriving our connection request rate. And W is how long, on average, a customer spends in the shop. That's our average transaction response time.
Okay, I think I'm getting it.
So L above U basically tells you if you know how fast requests are coming in and how long they stick around. W, you can predict how many connections L you'll probably need at any given moment to keep things flowing without a queue forming.
So for our e-commerce site example.
Right. If your average database transaction you takes, say, 100 milliseconds, that's 0.1 seconds, and you have 50 new connection requests per second, then L, the average number of connections simultaneously in use, is just 50 times 0.1, which is 5.
5, okay.
So that gives you a data-driven starting point for your pool size, at least under average load. It's really about proactive capacity planning, not just guessing.
That makes it much clearer. So it's about balancing demand with capacity, trying to avoid those queues. But what happens if demand suddenly spikes? Like during a flash sale on our e-commerce site, average load goes out the window.
Exactly. A connection pool, it acts like a bounded buffer, like a waiting room with limited chairs. If incoming requests for connections suddenly outstrip the available handlers, the connections in your pool, you're faced with a choice.
Okay.
You either start discarding traffic, just dropping requests, which is, a disaster for availability. People can't check out. Or you queue those requests.
Which most pools do, right?
Yeah, most well-designed connection pools will opt for queuing, thankfully. But the downside is this then directly increases your application's response time. Users are now waiting, sometimes timing out, just waiting for connection to free up.
Which leads to that sluggish feeling again.
Precisely. And this raises a really important question for developers. How do you even know this queuing is happening in production? You need to see it.
Right, that's where monitoring comes in. The source really emphasizes several practical monitoring metrics for connection pools. These seem absolutely crucial for, well, for provisioning and adapting to real traffic.
Hmm.
You want to keep an eye on kind of connection request count. That's like your early warning system for traffic spikes, yeah.
Definitely.
Then there's concurrent connection count, showing what's actually in use. And of course, things like maximum pool size, connection acquisition time, how long it takes to get a connection, retry attempts, which tells you if press had to wait, and connection lease time. Ignoring these metrics, it feels like driving blind.
Completely. You're just guessing about one of the most critical resources, optimizing SQL execution, batching and caching.
Okay, so once you have your connections humming along nicely, the next logical step is optimizing the SQL queries themselves. The book really dives deep into batch updates. What's the core benefit here? Maybe something developers often overlook.
Yeah, maybe the surprising fact about batching isn't just that it's faster, but how often developers simply forget to enable it or don't realize their framework isn't batching by default. You could be leaving massive performance gains, sometimes 10x, even 100x improvements, just sitting there waiting for a single configuration change.
Wow.
JDBC 2.0 introduced batch updates specifically to group multiple DML statements. Your inserts, updates, deletes into a single database request. The main benefit, dramatically reducing the number of those costly database round trips.
Because each round trip has network latency.
Exactly. Network latency overhead. So by bundling operations, you slash the overall transaction response time. And the source is explicit. Any insert, update, or delete statement can be batched.
And it's not just for simple statement objects, right? The book points out prepared statement is a much better fit for batching.
Absolutely. Prepared statement is crucial, not just for performance, but maybe even more importantly, for security. It allows for parameterized queries, which protects you against SQL injection attacks by safely binding the values.
Right, the classic security hole.
Yeah, and the book shows clear evidence. Prepared statement batch inserts outperform plain statement for the same data load. But here's the critical insight, the nuance. Finding the right batch size isn't trivial.
It's not just bigger is better.
No, definitely not. It's not a linear performance gain. Too small, and you're not getting the full benefit of reducing round trips. Too large, and you might risk exceeding network buffer limits or database limits or creating transactions that are just too big and hold locks for too long. It really requires careful measurement and tuning in your specific environment. No magic number.
Okay, measure, don't guess. Makes sense. Beyond batching, the book also discusses statement caching. This sounds like it could speed things up quite a bit by avoiding redundant work.
Oh, it absolutely can. When a database gets in SQL statement, it typically goes through these pretty expensive phases: parser, optimizer, and executor. The optimizer, that's particularly resource intensive.
That's the brain figuring out how to run the query.
Exactly. It's the database's brain, determining the most efficient execution plan. Like, should it use an index scan or a full table scan? What's the best order for joining these three tables? Stuff like that. Caching these execution plans means the database doesn't have to go through this costly optimization process every single time the same query structure runs. Huge win, especially for frequently executed statements.
So the database can effectively remember the efficient way to run a query. But then the book brings up something fascinating, that the execution plan can be bind sensitive. That sounds like it could throw a wrench in that whole remembering process. How does that work? Does it reduce the benefit of caching?
That's a great question, and it's a common point of confusion. Yes, the optimizer often relies on the actual values you provide for the bind parameters to figure out the truly optimal path. This is especially true when you have skewed data where values aren't evenly distributed in a column.
Skewed data? Like our e-commerce example.
Perfect example. Imagine our products table has a status column. Maybe 95% of products are available, but only 1% are out of stock. The optimizer might choose a very different plan for where status is available. Perhaps a full table scan is faster versus where status available stock, where an index scan would almost certainly be better.
Ah, okay. So the value changes the plan.
Right. Some databases use techniques like bind peaking. They literally peek at the parameter values before optimizing. Or even fancier stuff like adaptive cursor sharing, where they can actually manage multiple execution plans for a single parameterized statement, and they pick the best one based on the current parameter values they see.
So it doesn't kill caching, it just makes it smarter.
Exactly. It doesn't reduce the benefits of caching. It makes the caching more intelligent, more dynamic. It helps ensure the right plan gets used, even when the data characteristics for different parameter values vary wildly. Beyond raw SQL.rm and advanced strategies,
Okay, so once the database knows how to efficiently find the data using cached plans that adapt to parameters, the next performance hurdle is how efficiently you pull that data back into your application. That's where result set fetching comes in. The book stresses that fetching too many rows or too many columns can be a major performance killer. I've definitely seen apps slow to a crawl because of this.
Absolutely. The less is more principle applies directly here. And honestly, this is where many ORM users can run into trouble without realizing it.
How so?
Well, imagine on our e-commerce site, you want to display, say, 100 recent orders, and each order has maybe 20 order items associated with it. If you're not careful, especially with configurations like fetchtype.eager in your ORM mappings,
Eager loading. Yeah.
right, this can easily lead to a Cartesian product in the SQL query generated behind the scenes. This means instead of getting like 100 order rows and then maybe making separate queries for the 2,000 item rows, the database might actually produce 2,000 rows where each of the 100 orders is duplicated 20 times, once for every single order item.
Oh, wow. That's a lot of data.
It explodes the data transferred over the network, consumes way too much memory in your application, and often leads to those dreaded out-of-memory errors or just abysmal performance. Using SQL limit clauses or JDBC settings like max rows, these are crucial techniques to control the size of the result set coming back from the database and prevent that kind of data explosion. Fetch only what you need.
Right. Speaking of ORMs, the book spends a good chunk of time on JPA and Hibernate. What's the core problem they're trying to solve for developers, and why do they still matter so much in modern Java, even with these potential pitfalls like eager fetching?
Well, they primarily solve that fundamental impedance mismatch, that sort of philosophical difference between the object-oriented way we think in Java, objects, relationships, inheritance, and the relational model of databases, tables, rows, columns, foreign keys.
The classic mismatch.
Exactly. ORM tools like Hibernate automatically translate our object state changes, saving an object, updating its fields, loading related objects into the necessary SQL statements. This significantly boosts development speed, no question. You spend way less time writing that boilerplate JDBC code.
And JPA versus Hibernate.
Right, so JPA is the specification, the standard API and mapping rules defined by the Java community. Hibernate is one very powerful, very popular implementation of that specification. And understanding the details of that implementation, Hibernate's specifics, is often critical for performance. For instance, Hibernate offers transparent prepared statement batching.
Connecting back to batching.
Yes, it can be a game changer. Sometimes just by flipping a configuration property, Hibernate will automatically batch your inserts and updates for you if you set things up right.
Okay, so it sounds like a real double-edged sword. Huge convenience, speeds up development, but definitely has potential performance traps if you're not careful or aware of what's happening underneath.
That's a perfect way to put it.
The book highlights the persistence context as a right behind cache and talks about flushing. This feels like one of those abstract ORM concepts that has really big real-world implications, doesn't it?
It absolutely does. The persistence context is essentially Hibernate's first-level cache, and it's a crucial optimization. The critical insight here is that it delays writing entity state changes back to the database until the very last possible moment.
Right behind.
Right behind. This reduces the duration your application holds database locks, which can dramatically improve concurrency, fewer lock conflicts. But this right behind behavior introduces a really common and often overlooked consistency challenge.
Okay, what's the catch?
The catch is if you make some updates to an entity in your Java code, and then within the same transaction, you immediately execute a query that should see those changes, you might not.
Wait, really? Within the same transaction?
Yes. Unless you explicitly flush the persistence context before running that query, your query might hit the database before your changes have been written. So the query sees stale data. It's a subtle read-your-own-rights consistency trap that catches a lot of developers off guard. You have to tell Hibernate, hey, push my changes now before I run this query.
That's a huge potential pitfall. Wow. Okay, another critical area the book touches on is relationships in ORMs, defining how Java objects relate to each other and their database tables. I've definitely seen some messy many-tune and one-to-many setups cause headaches. What are the key pitfalls or best practices there?
Yeah, understanding how JPA actually maps those object relationships to database foreign keys is just foundational. The book explains a really common pitfall, unidirectional at one-to-many associations.
Just having the list on the one side.
Exactly. In Hibernate, that's often surprisingly inefficient. Why? Because without a foreign key column on the many-side table pointing back to the one-side table, Hibernate often has to create an extra invisible junction table in the database just to manage that one-to-many association.
An extra table, just for that.
Yeah, which leads to more complex join queries and increased index memory usage, even for what seems like a simple conceptual relationship. Generally bidirectional associations where you map both sides, especially making sure the at-many-tune side, the many side that naturally holds the foreign key, is marked as the owner of the relationship. That's usually far more efficient.
Okay, that makes sense. Let the side with the foreign key manage it.
Pretty much. And this naturally raises an important related question. How do the identifiers themselves, the primary keys, affect performance in this whole ORM and relationship context?
That's a great point. The book discusses the choice between, say, UUID versus numerical identifiers, and also the different ID generation strategies like database identity columns versus sequences. What are the practical trade-offs there for developers building these applications?
Well, generally, numerical surrogate keys, just simple incrementing numbers like longs or integers, are almost always preferred over UUIDs. They have a smaller memory footprint, both in Java and in the database index, and crucially, they lead to better index performance, especially if they are sequential. Clustered indexes love sequential inserts.
Right, UUIDs are random, can cause index fragmentation.
Exactly. But then, how you generate those numerical IDs becomes critical. The identity generator strategy in JPA, where the database automatically assigns the ID after the row is inserted, well, that often disables JDBC batch updates in Hibernate.
Why? That seems counterintuitive.
Because Hibernate needs to know the ID of the entity immediately after the insert happens, so it can manage relationships in its persistence context, maybe set foreign keys on related objects you also just created. Since identity only gives the ID after the insert commits, Hibernate has to execute each insert individually to get that ID back right away. No batching possible.
Okay, so what's the alternative for batching?
Sequence generators. With sequences, Hibernate can ask the database for a whole batch of IDs before doing the inserts. It fetches, say, 50 IDs from the sequence, uses them to prepare 50 insert statements in memory, and then sends them all off as a single JDBC batch.
Much better for throughput.
Significantly more performant for high-volume inserts, yes. Plus, database sequences themselves use very lightweight, highly concurrent synchronization mechanisms internally. They generally scale much better under high load than the row-level locking that's often involved in older table-based generator strategies. So yeah, choosing the right ID generation strategy can have this surprising ripple effect on your batching performance and overall throughput.
So that single choice identity versus sequence can either turbocharge or totally cripple your batch inserts.
Wow. Okay. The book then moves into concurrency control and transactions, emphasizing the ACT properties and isolation levels. This is where data integrity really gets serious, right? Indeed. Transaction isolation is all about ensuring data integrity when you have multiple concurrent connections accessing and, crucially, modifying the same data. You want predictable results. The book describes the common anomalies that can occur at lower, more performant, but less strict isolation levels.
Wait, what kind of anomalies?
Well, there's dirty reads that's reading data that another transaction has changed but hasn't committed yet, so it might get rolled back, and you read data that never technically existed. There's non-repeatable reads. You read the same row twice in your transaction, but get different values because another transaction committed an update in between your reads.
Okay.
And phantom reads, where you run the same query twice, like find all orders for customer X, and you get a different set of rows the second time because another transaction inserted or deleted an order for that customer. The book also covers trickier ones like write skew and lost update, which are subtle bugs often prevented by using higher isolation levels or employing explicit locking mechanisms.
So understanding these helps you choose the right isolation level, that trade-off between performance and consistency.
Exactly. It helps you pick the right level for your application-specific needs, balancing how much performance you need versus how much potential data inconsistency you can tolerate.
The book even calls out the open session in view anti-pattern. Why is that considered problematic?
I've definitely seen that pattern floating around online, often presented as a solution to the lazy initialization exception.
Open session in view, yes. A classic example of treating the symptom, not the cause. It attempts to solve lazy initialization exception, that error you get when you try to access a lazily loaded collection after the Hibernate session is closed, by basically keeping the persistence context, the session, open for the entire duration of the web request, often extending right into the view rendering layer like JSPs or time leaf templates.
Seems convenient, maybe. It might seem convenient initially, but it's really a Band-Aid, not a proper cure, and it introduces a whole host of other problems. First, it badly blurs the architectural lines between your service layer and your UI layer. You can end up with database queries being triggered unexpectedly from within your view code, which is a nightmare for debugging and maintenance.
Yikes.
Yeah. It also encourages running in auto-commit mode for requests that aren't explicitly wrapped in a transaction, which adds I/O overhead because the database has to flush its logs more frequently. And maybe most importantly, it makes integration testing significantly harder because you have this implicit session management tied to the web request lifecycle. Fundamentally, it just hides the real problem, which is usually improper transaction boundaries or fetching strategies. It's definitely a design smell you should actively avoid.
Okay, good warning. What about explicit locking then, like pessimistic and optimistic locking? When would you choose one over the other to handle concurrency conflicts directly?
Right? These are your tools for actively preventing data conflicts. When you know multiple users or processes might try to modify the same record around the same time. Optimistic locking is usually the first choice if conflicts are expected to be relatively rare.
How does it work?
It typically relies on a special version column in your database table, or sometimes by comparing all the columns that changed. When you read the data, you get the current version number. When you try to update it, you include that version number in the UPDate statement's where clause. If another transaction snuck in and updated the record first, incrementing the version number, your UPDate statement won't find a matching row with the version you read, and the ORM throws an optimistic lock exception.
So it detects the conflict after the fact.
Exactly. It detects the conflict without holding long-term database logs, which is great for throughput and concurrency when conflicts aren't happening constantly. Think about two users trying to edit the same wiki page. The first one to save wins. The second gets an error saying the page was modified.
Okay. And pessimistic locking?
Pessimistic locking is the opposite approach. It assumes conflicts are likely, or the cost of a conflict is very high. It uses database row-level locks, often via SQL clauses like select for update, to explicitly prevent any other transaction from modifying or sometimes even reading the locked rows until your transaction commits or rolls back.
So it blocks others.
Yes, it blocks other transactions. This is suitable for scenarios where conflicts are highly probable, or data integrity is absolute paramount, and you must prevent anyone else from touching that data while you're working with it. Think about transferring money between bank accounts. You want to lock both accounts involved to ensure the operation is atomic. You can even set timeouts on these locks to prevent a transaction from blocking others indefinitely if something goes wrong. It's really about choosing the right strategy based on the likelihood and cost of conflicts in your specific use case. The bigger picture. Monitoring and alternative tools.
Okay, all these optimizations, pooling, batching, caching, locking strategies, they're great in theory. But how do you actually know if they're working effectively for our sluggish e-commerce application? The book circles back, quite rightly, to monitoring. What should we really be looking at?
You're absolutely right. Monitoring is crucial. You can't optimize what you can't measure. And maybe the surprising fact here is that Hibernate actually has a pretty powerful built-in statistics collector that many developers just don't even know exists.
Really? Built in?
Yeah. By simply enabling a configuration property, Hibernate.generative statistics, and setting up your logging correctly, you can get Hibernate to emit invaluable notifications. Things related to database connection usage, session metrics, entity state transitions, loads, updates, inserts, deletes, second-level cache hits and misses.
Wow, that sounds incredibly useful.
It gives you real-time reports on exactly how your application is interacting with the persistence layer and the database. And for logging the actual SQL statements themselves, the book mentions using proxy data sources like DataSource Proxy or P6Spy.
What do those do?
These tools wrap your actual database connection pool. They intercept all the JDBC calls going to the database. This lets them log the exact SQL being executed, crucially, including the actual bind parameter values being used. That's invaluable for debugging those bind-sensitive performance issues we talked about earlier. They can also detect and flag long-running queries that might be causing bottlenecks. It's truly essential tooling for any developer serious about database performance.
Okay, that sounds indispensable. Finally, the book briefly touches on JOQ as an alternative, or maybe a complement, to ORMs like Hibernate for certain tasks. Is this an either situation, or is there a time and place for both?
That's a perfect question to kind of wrap things up, because it's absolutely not an either situation. This is where I think it gets really interesting for experienced developers. JOQ is a query builder framework. Its main emphasis is on generating type-safe SQL. Yeah, meaning You write your queries using a Java API that reflects your database schema, and the compiler helps ensure your SQL is syntactically correct and uses the right types. While ORMs, like Hibernate, excel at managing object state transitions and abstracting away common CRUD operations, JOQ is often ideal for scenarios like complex reporting, analytics, maybe ETL processes.
Things that aren't just simple object mapping.
Exactly. Queries that need to leverage powerful, often database-specific features that JPA or Hibernate might not fully support, or might support in a clunky or non-performant way. Think about things like window functions for complex analytics, common table expressions, CTEs, for breaking down queries, or intricate multi-table joins and aggregations. JOQ essentially embraces the full power and expressiveness of SQL, rather than trying to abstract it all away behind an object model.
So it's really about picking the right tool for the right job. Use the ORM for object management, maybe reach for JOQ for complex SQL-heavy tasks.
Precisely. It allows you to get the best of both worlds, using the strengths of each tool where they fit best.
Outro. We've really gone on quite a deep dive today, haven't we? From the really low-level mechanics of database connections and SQL execution, all the way up to the higher-level world of ORMs, concurrency strategies, and even alternative tools like JOQ. I think the key takeaway here is that high performance in Java persistence isn't about finding one single magic bullet. It's much more about a combination of understanding how your application interacts with the database at all these different layers. It feels like a journey of continuous refinement.
Indeed. It really is a continuous dance between the convenience you get from abstraction layers like Hibernate and harnessing the raw power and specific features of your database. Choosing the right identifier generation strategy matters. Carefully managing your fetching mechanisms, avoiding those Cartesian products, proactively applying batch updates where possible, and critically, constantly monitoring your application's database interactions to see what's actually happening. Remember the quote from the book about the optimizer?
The one about the fixed time budget.
Yeah. The more time is spent on finding the best possible execution plan, the higher the transaction response time will get. So the optimizer has a fixed time budget for finding a reasonable plan. It's all about being smart and informed, not just trying brute force, making the optimizer's job easier.
So what does this all mean for you, the listener, and your own applications back at work? It means that being an informed developer, understanding these underlying mechanics, is probably your single best performance optimization technique. It allows you to make those smart trade-offs, to diagnose the real issues when things get slow, and ultimately to build systems that truly excel and provide that smooth user experience even during that unexpected flash sale. So for your own next steps, maybe consider, how do your applications currently handle database connection pooling? Are you actively monitoring those key metrics we discussed, like acquisition time and queue length, to predict and prevent bottlenecks before users complain? And maybe for your next complex reporting feature or that big data processing job, are you consciously choosing the right tools, sticking with JP Hibernate, or perhaps exploring something like JOQ for its SQL power for your specific data access patterns? The tools are out there, but understanding their nuances, their strengths and weaknesses, that's the key. That's it for this deep dive. We really hope you've gained some valuable, practical nuggets of knowledge to apply to your own projects. Until next time.